All right. Happy Thursday. Sorry to miss you Tuesday. It's been a rough week, so don't get too close. Um, we're going to look at array-based sequences. This actually goes pretty quick in Python because we have the built-in list already. Um, it, it doesn't translate quite as well to fixed array sizes that usually array-based sequences use here, but we can do that. We fire up PyCharm and we get a new project going. Oh no, there we go. Make sure I get it in the right folder here. This week 4, I think, already? 4, 5? Array-based sequences. So in other languages, there is a fixed size array, which you declare, hey, I want space for 10 things, and it only has room for 10 things. It's not expandable like our Python list is. Um, and there's some stuff that happens behind the scenes to give you enough space to store 10 things. Right? It sizes it appropriately. It works pretty well. So it's pretty efficient at that point if you know how big it's supposed to be here. Where's my main file? Now, the Python list, because it's expandable, already does all of these smart things that we're going to have to figure out how to do with a fixed sized list here. Uh, so we can take a look at that while that loads. Size of object. Sys get size of. Okay, good. Maybe we'll get a main file. It's still updating. Did I not check the box? I don't remember if I checked the box now. All right, so if we were to make a list of numbers here, and then we're going to get the size of it and see how many bytes of memory this numbers is using. Right now, it's not going to be how many numbers are inside of it. It's going to be how much space it's taking up in memory. So when we use lists here, the reason why they're so fast and the reason why we can get at things by index is it's allocated enough memory to hold that many items here. And the first spot here is where the first item is. Right? That's why we always start with index 0. It's at the memory address of where it starts. That's going to be 0. So numbers, we'll go add a bunch of numbers here. So for n in range 100, numbers append n, we'll add the n to it. So in the 0th spot, we'll add a 0 and then a 1 and a 1 and 2, 3, on and on and on. So wherever this memory address is, that's where the first item is stored. The next item is stored at that amount of memory plus 1, and that amount of memory plus 2, that amount of memory plus 3. So it's the size of the items here, which are just references. It works out pretty nice here because it's going to store references to other items here. So if we check the size, we want to print size of, get size of numbers, and then we can do a little pretty formatted string here. So with and items size is get size. Um, sure, actually let's bump that down. Let's do it first. So with nothing here, sure. And then we'll see the way this thing grows here, it grows in small chunks. So before we put anything in, it's got room for one thing, and it's got room for a couple things, and it's got room for a couple more things. So it stays the same size as we're adding here until it reaches a certain point and has to grow. So it's oversized initially so that you can add a couple items here without having to go and resize this. When you take items out of a fixed array and have to put them into another array, that's a very slow operation. And we talked a little bit very briefly around how slow things are, and that's our time complexity. So the more n items you have here, if you have to take them from one array and put them into a bigger array, it takes n operations. You have to take this memory address, move it over here. Take this memory address, move it over here. Take this memory address, move it over here. Take this value, move it over here, right? So we have to move n things here. So most of the time, when we add an item to our array, it's really quick because we've got space. Occasionally, we'll go ahead and have to resize the array. Now, there's some really cool math that happens behind the scenes for what size these things should be and how we do this efficiently here. Um, but essentially, we do some fancy hand waving with our math here. Let me draw a little picture here. This is fun. So if I have a fixed size array here, right, and I'm going to add some items to it. So when we talk about complexity and time complexity, it's how many operations does it take in terms of n items here. So if I have room for two things here, right, I can drop an item in and it just takes one operation, right? Goes really quick with one item. For two items, I can drop it in, just takes one operation. At the point when I need to resize, then if I want to add that third item, well, okay, it's going to take all the previous steps here, right? And then one more to add that item. So this one will be a slow operation because it has to resize. And then if I've doubled my size here, then I'll have room for 4, 5, and 6, right? Those ones will just take one operation because I've made some extra rooms. I made a bigger array, move them over. When I run out of room here, I'll have to move the previous 8 things. So this one will take 8 operations to move all the items into a new array here. And then the next 8 will be fast because I've doubled my size. So if we're doubling our capacity every time here, most of our operations are fast here, and then occasionally it's slow. And what's cool here, if you want to visualize this, you can imagine this, the bar getting like shifted this way here and laying down. So if we're going to average how long this takes here, instead of this operation 3 being slow, operations 3, 4, 5, and 6 are 2. Right? And this bar here, instead of operation 7 being ridiculously slow, you just kind of lay it down flat here and pretend all these operations are 2. So if we look at the average time that it takes to add something to a fixed size array, even if we have to resize, on average, it's still going to be 2 operations. It'll be constant here. And constant's our big fancy word for it doesn't matter how many n you have, it just takes some fixed amount of time. It could be 15 things my computer has to do, it could be 100 things my computer has to do, but it doesn't change in terms of how many items I have in my collection. And that's what we get with our Python lists here. It will grow. The number's not exactly half. There's some really smart people who've done this sort of math here and figured out what's the efficient way for growing these things. But essentially, we can average out the time that it takes here so that adding, so we could say on average, or this big O here notation, that's our I don't know why, there's a couple algorithm, complexity, big O. Yeah, the big O complexity is the how long it's going to take here. So this one is like O of 1 is constant. Now, the fun thing in computer science math land, anything that is constant, we'll just say is O of 1. We don't need to say it's O of 10, it's O of 20, it's O of 30, it's just O of 1, it's a constant. It doesn't matter if it's 7 operations, we'll just say it's O of 1. Right? If you can get a little bit faster, you can be logarithmic in n, like when we did our searching, our recursive binary search, right? That's going to be a logarithmic number of searches to find that because we cut it in half every time, we cut it in half every time, we cut it in half every time. So you can have a billion items and still be able to find it within 32 searches. Something pretty quick here. And then O of n, right, is the more n I have, the longer it takes, and then it gets only worse on top of that. N times log n squared, 2 to the n, and n factorial. There's some pretty bad speeds for these sorts of things here. So again, this is we call it big O. I don't know who came up with it here, but this is the worst case here. Average time is, what do we call that one? On an average. There's another term for it here, and I don't remember because I don't ever use the term. Um, yeah, usually it's big O. Okay, that's what I thought. That's fine. So on average, O of 1 will be constant for adding because we can do that fancy averaging here for adding items. Now, with a array that's sequential, if we want to take something out of that array, so if I were to take my numbers and were to call remove, hey, let's remove the 0 here. Well, what has to happen if I have a bunch of numbers in my Python list here? Because they're all index-based, right? I have a 0, a 1, and a 2, and a 3 and a 4. If I want to remove the 0, what has to happen? Everything has to shift down a spot. And this one shifts down a spot, this one shifts down a spot, this one shifts down a spot. As many items as I have to get shifted down here, and they all change indexes here. So removing something from a list here is going to take n operations. Now, there's some fancy math here. You could say, hey, k is the index here, and it's really n minus k. So if you take something from the front, it's going to take more. If you take something from the end, or the end, this direction for you guys, right, it'll take less operations. Like removing the last thing, nothing has to shift, right? If I remove the middle thing, half of them have to shift. If I remove the first thing, all of them have to shift. So turns out on average, that's still O of n. It's like O of half of n, but it's still n, right? We essentially get to throw away the coefficients there. So O of half n is still an O of n operation. It still grows linearly, even if it's like half of n linear. Does that part? It's a little bit funky with our math here, but works out pretty well. So removing something, then, on average, removing, this is O of n operations. Okay, we throw away the constant coefficient. Did I spell coefficient wrong? Is it just one O? No? Coefficient? Two Fs? Two Fs, one O. There's double letters in there that confuse me here. So removing something is pretty slow, right? Finding an item in an unsorted list here. So if we wanted to say, hey, let's call numbers dot uh, index of, right? I want the index of where, value 5 or something. So on average, finding. Now it's unsorted, so it has to look at every item. The item might be close to the front. It's again this n minus k thing, or it's k minus n, right? Because if it's at the front, it takes less. Um, if it's at the end, you'd have to look at 50 items or 100 items or 1,000 items, whatever it is here. So again, this one is an O of an operation. This one, bigger it is, the slower it is to find something inside of that collection. Right? If you got 1,000 things, sure. If you got a million things, way slower. If you got a billion things, even slower. Right? So it just gets slower the more n we have here. So with these arrays, even if they're dynamic in size, it's still slow to find something. It's slow to remove something, but it's pretty quick to add. Right? So these are good at adding, and they're good at accessing anything by index. So if we're to access an item by index here, so like numbers at 10 or something, right? If we just wanted to say print it out or change the value, right? Either one here. Now this one, because it's the sequential sequence of memory addresses, right? We've got some big chunk of memory where I can store all these things here. This one happens in O of 1. It doesn't matter if I have a million things. It doesn't matter if I have 10 things. I take the index and I can do my little arithmetic. Where does it start? Times how many indexes do you want in? What's the size of the space here? And I can get right to that location to read. So reads then, accessing or reading or updating is really fast. So our fixed size arrays or dynamic sized arrays are really good at reading. They're really good at adding, right? They're not so good at removing and finding. So when we start looking at all these different data structures, right, we got this whole list of data structures we're going to start looking at here. Some of them are fast at some things and some of them are slow at some things. Right? And that's going to be a trade-off we're going to look at. So when we design solutions, we now have tools that are good at some things and bad at other things. So we want to pick the right tool for the problem that we're trying to solve. And that's why we spend so much time studying these things. Writing them is not all that interesting. I got to be honest here. It's a little bit boring. They've already been written by really smart people. We're not going to do better. Right? If you want to do better, go get a PhD, and that will be your life's work of, incrementally making this thing like 2% faster would be huge. And really smart people do that, which is cool. But we want to know when we're solving problems here, what's the right tool to use? Right? Not everything is a nail just because we have a hammer. Right? Sometimes we need to use some other tools. Um, so if we wanted to do this ourselves and make our own fixed size array, which again is a bit of an annoying thought exercise, but we can here. So let's make a new module here. So let's call this our um, fixed sized array. They don't use underscores. How do they do that? Fixed size array. So we're going to make a class for this fixed size array, and we're going to init here. Now, internally, we're going to have, because there's not really another good way to do this here, we'll have our own data list here, which again, it's not, it's a little silly to do this in Python. I'm sorry. There's some other ways. The book will take you through using the primitive type. You don't really gain anything by using the primitive type, and you're not going to use your own data structure for this anyway. So we're just going to call it a list here. What we're going to do is we're going to have a self dot max size. And let's just size it as 10. So what we want here is I'm going to put none times 10. So I want a nothing here, a null reference, nothing there, but space for 10 things in my data. So I've got room to store 10 things, okay? And then self dot number of items starts at 0. I have no items currently in my list here. I've got room for 10 things here, and I've got a list with 10 spaces here. So I'm going to manage the own doubling. Again, it's stupid, but it's okay. Just the exercise. And then things we can do here, we can have an append, right, given some item here. And then we can have a remove given some item here, or that's the value, right, you want to remove. And then we can define the get given an index here, right? How can we remove these things? How can we get them? Now, Python has some built-in special functions here. There's a set item here. I don't like using them. You can go through and do them. We'll do them when we do a dictionary. At some point, we make our own dictionary. It's not for our purposes. Again, we're just sort of looking at should these things be fast or should these things be slow, right? So this one we wanted on average. This should have been O of 1, right? Because most of the time it'll be fast. Occasionally it'll be slow. But if we average it out, they're all just 2 operations. Right, removing an item we know is going to be really slow. So this one here we know is going to be O of n. The more n I have here, the longer it's going to take. Right, and getting an item by index here, this one should be super fast. Right, so this should be O of 1 because I can get at anything by index. Right, and then what do we want it? A find, I think. O of that was going to be slow to go and find something here. So find a value here would again be kind of slow. So looking at how we do these different ones here. So we need to see, do we have room to store this item here? So if my number of items is equal to my max size, I don't have room. And I'm going to have to resize here. So I can check if self.max size is equal to self.number of items. Then I'm going to have to go and resize. We'll call self.resize. And we'll make a little helper function for that. Aside from resizing then, assuming I have room, then I'm going to take my self.data at the self.number of items and assign it the item. Okay, so if I've got room to put something, I'll go put it at that index here of how many items I have. When I have 0 items, it goes in the 0th index. And when I have 5 items, the next one goes in the 5th index to become the 6th item. Then my self.number of items goes up by 1. I've added 1. So we're going to put it in this. This is always going to be then, so self.number of items items is the next available index, right? So that way I know, oh my goodness, if it matches my max size, I don't have room here because I can fit 10 things, but I have indexes 0 through 9. There's not room here. I have to go resize, okay? So that's what that one does for me here. To remove an item, we have to go find that value, right? So we have to go see what index it's in and then shift all the other ones down by 1. It's really tedious here, but that's okay. So we'll say for index in range, self.number of items. Now, I only need to look at the number of item slots. I don't need to look at all of the items in my data because the couple at the end should be blank. Sorry, the end, the side for you guys, should be blank. Probably will be blank. I might be completely at max and I might have a couple blanks. So I only need to say when I have 5 items, check indexes 0, 1, 2, 3, and 4. Right? And I have 10 items, indexes 0 through 9. If I have 0 items, I don't have to check anything. Right? So we're going to go picking each one of those indexes. We're going to look to see, did we find it? Right? So if my self dot data at the index, if that's equal to the value I'm looking for, then I found it here, and I need to go shift everything else down into this spot here. So the shifting part gets to be a little bit annoying here. So if we found it, then we want to go for um, index shift in range. Now we're going to start at the index +1, and we want to go up to self.number of items. Right? So because I'm going to shift them back by 1 here, I'm going to go wherever I was +1, and then up to the last one that I have here. And then we'll take self.data at the index to shift -1 equals the self.data at the index to shift. So take the thing I'm moving, move it back 1, right? Because I'm starting 1 ahead of where I was. So we can remove that value here, go to the end, and pop up everything back by 1. Next one back by 1, next one back by 1, next one back by 1, right? And when that one's done, we can break our loop. The outer loop here that says stop, right? So once we find it, go to the end, shifting things, and then stop. We're done here. If we don't find it, right, at the end here, we could raise some sort of errors here. That might be nice. So if you break a loop, remember you don't get an else here. Python's kind of weird here. You can add an else in a loop here. So we can raise a value error, item not found. Right? So if you try and remove something and it doesn't exist here, well, it's just fail. So we can use some funky syntax for that here. Appending should be fine. We'll get to resize a little bit here. But then once I've removed something, I need to make sure I take my self.number of items down by 1. Right? Make sure now I have one less thing in my collection here. To go get an item by index, we're just going to return self.data at that index. That one's really quick here. And to go find something, we're going to look at every single item. So for index in range, self.number of items, if the self.data at the index is equal to the value, return the index. If we haven't returned something, we can either raise a value error or I think that's really easy. Item not found, or not, I will just say not found, right? So if we find the index, great. Get, great, good, remove something, fine. All right, so to resize then, we need to add a little helper function here. Define resize here. We need to make a new storage array. So we'll have new data equals, now we need none times my self.max size times 2, or really let's just increase our max size first. We'll make this easy. So self max size multiplied by 2 here. So we'll double our size, make a new array, right? And then for index in range, self dot number of items here, let's take my self dot data at the index. I'm sorry, self dot new data. So new data at the index is equal to self dot data at the index. So copy it over. Go to the old one, copy to the new one. Go to the old one, copy to the new one. Go to the old one, copy to the new one. So this one takes n operations, right? No matter how many n items I have, it will take n operations. I have to literally copy every single item over to the new list, copy to the new list, copy to the new list here. And then when I'm done here, I'm going to say self.data equals the new data, right? Just replace the old array with the new one. Copy everything over, get rid of the old one, right? So I can resize myself, okay? And then I probably want here, now this one's kind of fun. You can have a length. You can define the length function. We're going to return self.number of items. So this tells you the length of an item when I use len, right? You could also have like the size of, this one's kind of a fun helper function here. That part makes sense? And we go through it a little quick. It's a silly thought exercise to look at why these things are slow, why they're what they're slow at, and why they're fast and what they're fast at. Because I can get at things by memory address really quick. Resizing is slow. I have to make more space here. Uh, on average, it's pretty quick, right? When I add stuff, so we can try and use it then with our own fixed size array. So let's do that again. So we'll take a from fixed size array, import fixed size array. And let's go repeat this process with our fixed size array. So we want a fixed size array equals a fixed size array. So we'll make one here, and then for n in range 100, let's go append the item and get the size. That's our fixed size array. We'll append, and then we're going to get the size of our fixed size array. Let's see. Size is 48. Size is 48. Size is 48. The object itself here, when I make an instance of fixed size array, what it stores is an address of a list, its max size, and its number of items. It's just storing the address of a list. The list itself is stored somewhere else. Wherever that's stored has its own size, right? So the fixed size array itself, how much memory it takes up is much less because this list is not inside of it, right? It's just where does it live? So it knows where it lives. So if we want to check the size of the fixed size array dot data, which again, you're not supposed to do this, you're not supposed to access private attributes, but Python's like, sure, go for it here. Now this one we'll see should change in size here. Here we go. So it stays at 136 for the first couple items here, right? And then it goes to 216 for a couple items, and then we're at 376 for a while here, and then we go to 676, right, for a while, because we've sized it up to a certain size, right? Uh, right, up to 80. So we're doubling, right? Again, there's some fancy math to find out the actual efficient thing here. Less than doubling, you don't always get exactly 2 ads on average, right? Sometimes it takes a little more. There's again, the math hurts my head behind how do you optimize that sort of thing. But one takeaway we get from that is if you know you're going to have 1,000 things in your list, it's faster to just start with 1,000 spaces here when you make the list rather than having to make it resize every bunch of items. So you can pre-size lists and arrays to as big as they're supposed to be to save you a little bit of time. So let's say an optimization we can do in our code. Hey, if I know I'm going to read in 1,000,000 data points, don't bother having to copy 500,000 and 250,000. Like, don't make it double every time. Just make room for 1,000,000 data points, and then you can read all 1,000,000 in without having any of the slowness in addition to reading the 1,000,000 in. So it does get to be important when we're working with large data sets that we're making sure we're sizing our data structures appropriately. Those small little optimizations do help. They add up here. But that sort of stuff is a bit of a silly exercise here because we already have a Python list and it does all of that for us, right? So reinventing the wheel is not very fun, but we could, if we wanted to, build our own sort of array like that. Yeah.
The time you ran it before this, one of the times, one like when I was doing the different item sizes, there was one row where it was just a size by itself, like it wasn't like a bunch in a row.
For the regular Python
Yeah,
list,
it was like
yeah, the first time,
where it said like the 156 or yeah, I think it was that one. There was just one where it was just the one number and it wasn't repeated like the other ones, but it wasn't the first number in the list. I don't think.
oh,
I could be wrong.
it usually repeats itself for a while, if I recall.
Unless we saw previous code
Yeah.
from when you ran it before and that, and I just assumed
I think it's just the very first time before we add anything to it. It's the smallest.
that's what it was. I just saw the previous code or something.
Okay. Yeah, I think usually we'll just take the first one and then it will start getting bigger as it goes. Um, all right. That's our list here. All right. Do you want to go over the project that was due today, right? Our project 0. And then we got to talk about the next project. Did I put 2 p.m.? 2 p.m. is right. Okay. I don't know what's happening right now, guys. Oh, man. Okay. Should we go over project 0? All right, cool. So we fire up a new project. Call this one project 0. Our silly little game simulator here, or game classes, right? We didn't need a main, right? All we needed was our modules here, our classes here. So we'll have a class for unit, right? That's our base type here. And now unit has to know a couple things, right? It has a bunch of attributes here. So for unit, we need to know a couple things. Oh my goodness, that does not copy paste very well. That's okay. So we'll define in the init here that these probably get set in the init. Now, it doesn't specify, right, that you have to set them in the init here. So you could have had a bunch of set functions. It's going to be really tedious, and they probably don't change very often. So it might not make sense to have range be changeable. Maybe it does change, right? Again, that's a game design thing we can work on later. Not too big of a deal. I think it's easiest to just pass them in to an init method here. So we can pass in an attack power, my goodness, a hit points, a range, a X and a Y, the team, right? The is alive, we know, right? Right? And then we can go set all those things here. Now, hit points might actually be passed in as the max hit points. And then you could set that. That might be a little easier. We'll call it max hit points. So self dot attack power is the attack power. Self dot max hit points is the max hit points. And then self dot hit points, right? Your regular hit points or current hit points, whatever you want to call it here, would also be the max, probably. Max hit points. Self dot range be the range. Self dot x position would be the x here, and self dot y position would be the y. Right, so we want these to be hidden here in our team. Self dot team is the team. And then if you wanted to use the Boolean for if you're alive or not, great. Or we could just say, hey, if I have not 0 hit points or more than 0 hit points, I'm alive. Either way is going to be okay here, right? We can just look for it on the fly, or we can add an attribute. Not the end of the world either way there. Right, then things that we do here, we can attack and we can move. Right? And then whatever other gets we need. So we probably need a way to get all of these things back out here. So again, writing a bunch of get functions is not super exciting here. So I'm going to be lazy here and go over to the chatbot and ask for some get functions here. Right? Get functions for this class here, paste it in, and then I'll say I did that here. Right? Get functions for class. Right? And then it should. Okay, there we go. I absolutely adore the chatbot here. Thank you for the comment that this is the getter for attack power. This is why I hate comments, right? That's not helpful here. It's just we burned electricity, extra electricity for that here, and now I'm a little sad about it here. All right, a bunch of gets. This is not the interesting piece here. So hopefully you used a chatbot or had some fun typing here. That one's okay. All right, so now I have all the gets here. We can get all of our values back out. Now, when we attack something, we need to see, should we actually attack this target, right? So given some target here, right? So we need to know, is it within range? And is it a team that we should attack, right? And those are things we're going to do a lot of different times here, so we can make some helper functions, right? Again, you don't have to, but these will work out pretty nice here. And then if I have a helper function for is within range, I can use that later on because I know other classes will do some things, right, if their units are within range, essentially. So we're going to define is within range given another target here. So we can return, right? This is just a true or false statement here. This is my self.range is greater than or equal to, now the triangle theory, right? So I'm going to take my self.x position minus the target dot get x position, or just underscore, right? Get it there x position. It's a little bit bad form to use their private attribute, but it's the same class here, so it doesn't matter one way or the other. But if I use the get x position, then it stopped yelling at me. And we can tell Python, hey, this thing is a unit, by the way, and we'll get a little bit better type ahead suggestions here. So we'll take that squared, right, plus the We bump it down a line here, sorry. Y positions squared. Um, Y position, difference of the Y position squared, right? And then all of that, then we want math.square root of. Root of that one there, right? That should get us our distance between 2 points. Is that right? A squared plus b squared equals c squared. Let me just reverse that. Okay, you guys weren't looking at me like, or you're looking at me like I'm crazy, but I think that works for us. Okay, thank you. Okay. I'm a little out of it right now, so good to know. All right, so if that's range is greater than or equal to that, right, we have enough range to get to the target, right? They're within range. Um, why does it not like unit? Yeah, maybe because I didn't finish this one here. All right, so if self dot is within range, given the target, right, and self dot should attack the target, then we'll go do that thing. So pack, there we go, pack, uh, should attack. Oops, a target, which is a unit here. We're going to check. So if self.team is equal to chaotic, we attack. Chaotic, chaotic, right? We attack anybody, doesn't matter, right? Or self.team does not equal the target.getTeam. Right? If we're a chaotic, we attack everybody, or if we're not the same team, we attack, right? So really that's just a return, right? But we broke it down in a nice little helper function here. Wouldn't have been too bad to throw that in here, but now I have it, right? All right, and then if we should attack, then we're going to take our target. Now, this needs a way to change their hit points, right? I didn't specify how we change it here. I just said make sure they stay between here. So at some point we need a way to change their hit points and manage this here. So you probably don't want, if you have to maintain a range here, we can't just give you public access to hit points because you can go set it to -20 or you can set it to 1,000,000,000, right? You need a function then that we control your access to this attribute to make sure that it stays within some sort of range here. So you could have a set hit points or you could have like a take damage here, whatever you think makes more sense here. It's fine. Let's go. You want take damage or you want set hit points? Set hit points? Yeah.
Can you just have it, like, just use the max function, 0 or whatever you're gonna set it to?
So we could use the function, but if I make that attribute public, I have no control over if other people accessing that attribute are going to use max. So the whole idea is that if it's a public attribute, they can go put it to whatever they want here. So you want some sort of public function that does that thing that takes it within max here, right? So that's why I marked all of these as private attributes here, so people shouldn't have direct access. We want them to use our public functions, so we can control access if we want here. So a set hit points, given a hit points here, then we'll take our self.hit points, assign it to the hit points, and then we can check. We can do our sanity checking. If self.hit points is less than 0, we'll set it to 0. And if our self.hit points is greater than the max, then we'll set it to the max. Right? And you could do other, use the max function, right? See which one is the correct one, use the min function, or we could do some other checking if you want here. It will get the same job done, right? We're saying if you went below 0, stop at 0. If you went above the max, stop at max. Right? Either way can work there. So then target dot set hit points, set hit points. We want to set their hit points to the target dot get hit points minus my self dot attack power, right? Take their hit points, subtract my attack power from that. That should be their new value for hit points, right? If it went negative, fine. I don't need to care. That should be okay. So that's how we attack them. And the defining move, then, well, I don't actually really know how to move right now, right? I know I can move, but each unit's going to move differently here. So this might be a case where I just want to raise an error here, not implement an error, and say, hey, I can't do that yet. It doesn't happen. I don't know how. I can define that in my subclasses here. That's an option. Why does it not like unit here? I think that should be fine. I'm super confused, but probably okay. So now, how do we know if any of it works? Well, we don't yet. So we need to go test it, right? So let's go to test here, create some new tests here. And again, I don't like to do all the gets individually here. I'm going to do an init and then make sure all the values are what I expect them to be here. But I definitely want to test attack. I can't really test move. We could test that it raises an error. Sure. At that point, that's a little bit silly, but that's okay. So really attack is the important one here. And then we'll do, I don't know, one. I'm just to get some code here, we'll call this one testing init here. So we're going to arrange, we're going to act, and we're going to assert, right? So we need a expected everything here, which is a little slow, but that's okay, right? So we have a bunch of these here. So we'll have an expected attack power, and I can copy that here and throw that one in. All right. So I don't know, like 5, 5, 5, 5, 5, 5, and team. And it doesn't really particularly matter here. And then we'll go make a unit, right? So then my unit, or from, I gotta go import. So from unit, import unit here. Unit equals a unit. And then we have to go give it all those things here. So we give it the expected attack power, we give it the max hit points. No, expected max hit points. Come on. Max hit points, right? And then we give it the, what's next here? Oh, where's my suggestion? Range, expected range. And then we give it the, is it X position? X position, expected Y position, and the expected team. Right? Very exciting. And then we get all the actuals here. Right? So then these will all be actuals. Actual. And we'll go get the values from our unit. So unit.get attack power, unit.get max hit points, unit.get hit points, unit.get range, unit.get X position, unit.get Y position, and unit.get team. Yay. All right. And then we can assert, did they match? So self.assert equal here, my expected and my actual. Probably go down the range here. That's fine. So we have 7 things, I think. I think that's probably right. Let's go with the attack power first. Attack power. And then we'll do the hit points. And then the actual hit points, good. The actual range, actual X position, actual Y position, actual team, yay. Expected max hit points, expected hit points, expected range, expected X position, expected Y position, and the expected team. All right, so hopefully this one runs. Right, that's our first test. All right, the init worked. So our gets all worked. We passed values, we got the values back out. Very exciting here. But now we want to test attack. Now this one, we want to make sure that it works. Now, is our code coverage going to be 100% from this running as long as we hit somebody? Yes. Right? If we don't attack them because they're not within range, my code still ran here, right? Like this line of code ran, I returned a true or false, but whether or not I want to test, did I do my logic right? It probably makes a lot of sense. I should test that explicitly. We're still going to have 100% code coverage with the one successful hit. So again, it's a little bit silly here, a little bit more of an art and a science here. So we'll say not within range here, just because I want to explicitly make sure that works as I'm expecting, not just that it does hit when they are within range, but that it doesn't hit when they're not within range, to make sure I did that right here. So we're going to arrange, but really need like 2 units. So we'll have a unit equal to unit here. Now, most of these values I don't really care about. So I care about the attack power. I care about the max hit points. I care about the range and the X and the Y. The team matters as well. So I guess all of them, matter here. Sorry. So then the target unit equals a unit, their attack power, max hit points, their range, their location, let's put them at 1, 1, and then their team, make them here. So if my attack power is 5 and they have 10 hit points, after I attack them here, if they're within range, oh, sorry, this was not within range. Let me put them, do a range of 1 here, put them further away here. Oh, I forgot there's supposed to be a default range. Yeah, square root of 2. Defaults are obnoxious here, sorry. So that's going to change up my whole init here, because that would have to be the last one then. And all right, that's fine. That's fine. Range equals math.square root of 2. All right, that'll work, but now I have to go change all of this here. That's a bummer. We just make sure we throw that in at the end there. All right, I think that'll work. All right, so now X and Y, team, us, and range. Okay, so we can leave the range, I guess, at square root of 2. Why not here? Team them here. So if it is at 5, 5, it's plenty far away here. It won't be able to hit here. So we're going to act here, or we should have an expected hit point. Sorry. So after we call attack, my expected hit points should still be 10, right? Because you didn't do any damage. You were too far away from my target here. And then we'll act. We'll call unit.attack the target unit. And then we'll go get the actual hit points. So actual hit points is my target unit dot get hit points. And then we'll assert. So assert equal my expected hit points and my actual hit points. Right? That one should be 10 and 10. Right? Let's give it a try. All right, that one passed. So now we'll do it when they are within range here. Attack actually works here then. So if you're close enough here, right? So maybe we give you a bigger range here or something. We'll just put them like 1 away. So if their range is 5 and they're 1 square away, definitely should be within range here. So then they should have 5 hit points left when they're done, right? Because they should have done 5 points of damage to them here because you were within range. That one seems pretty good. Again, we can add more tests for teams and things, or test that chaotic attacks everybody. If you wanted to be even more explicit, again, we've got 100% code coverage. It might be good to do here. And then hopefully you saw we've got these magic strings. That's probably a bad idea here. So let's make those like some constant values here. So we'll have chaotic equals chaotic. We'll have us equals us. And we'll have them equal them. So that I can use those values later, right? Instead of having to type them out here and possibly screw it up, right? So self.chaotic, and then other team is fine here. So when I go make a unit then, instead of us, I can say unit.us and unit.them, right? So I can set them that way. It's a little bit nicer than trying to pass strings in because who knows what we're going to do. Unit.us and unit.them. Excuse me. All right. So again, make sure I didn't break anything. Have all that working here. Seems to be okay so far with the unit class itself. That okay? All right. And then making subclasses, we'll get infantry. I guess we'll do that one first. Let's go add a module here for infantry. Separate modules for classes. Not everyone does. It's okay. So we're going to say from unit, import unit. And then we're going to write our class for infantry. And then it inherits from unit, right? It is a unit. So right off the bat, I need to have an init that passes a bunch of things here. So we're going to find my init function here. Now, I don't need to know a lot of things here, right? I still need to know my x position. I still need to know my y position, or x and y, right? But the other values here, I know what they're going to be, right? I know what my attack power is. I know what my hit points is, right? I know what my range is because I just get the default range. We didn't specify, so we keep the default here. So I'm going to call self super.init. Now, it needs to know, what is it? The attack power was 5. Goodness. I don't remember the order anymore here. Attack power, hit points. What do we say? Hit points was 5. We can pass the X, we can pass the Y. And then, oh, we need a team as well. Sorry, we need a team. pass the team. Is that right? Is that all we needed?
Range.
So the range should default, right?
Oh, for infantry, yeah.
Yeah, for infantry. So hit points, X, Y, team, and range. That should be enough, right? Why does it not like it? Unexpected arguments. Is it super dot in it? Yeah, I missed my parentheses. Sorry. There we go. Attack power, hit points, X, Y, team. Right? So we pass those in. Great. Now, what does infantry do that's different here? Well, it moves different. That's the only thing it does. So the only function we have to write in infantry is move. Attack still works the same as within range. All those things we get from unit here. So we're going to define move. Now, move needs a X and a Y, right? You have to tell me how many X or how many Y we're moving here. And then we can go change our locations, right? So we can quickly say, hey, if X and Y, we can raise a value error here. Can't move both. Now again, this is using Python being truthy, so I'm assuming one of these will be 0, and one of them will have a value, right? Um, and then no more than 5. You can't move both X and Y. And then if what the absolute value, I guess, right? So that's fabs for some reason. I don't know why of X is greater than 5 or fabs of Y is greater than 5. Can raise value error. Can't move more than 5 units. Is it? I have to import math? Import math. There we go.
What's the difference between apps and APF?
Do they have just ABS? Oh, okay. For some reason, I thought they didn't have the built-in ABS. Sorry. It's probably honestly, I have to Google Python abs versus abs. It's like it's based in C, I think, because we have to do this in C++, and I hate it. Um, Always returns it as a float. Okay, so you get a floating point value back here. That's very exciting here. So even if it's an super exciting here. Uh, sure. All right. Yeah, abs is easier. All right. So define move. Uh, oh, okay. So it's upset. We're overriding here, but we're telling it additional information, so it doesn't match. Right, there was move with no arguments, and then there's move with x and y. So probably should make move in the parent class take an x and a y, so that it does match here. We don't get confused about which move we should be using because this one doesn't actually do anything here. There we go. So if none of that happens, then I can take my self.x position plus equals the x here, and self.y position plus equals the y. I don't, one of them should be 0, so we'll do nothing here, but I don't even need to bother checking because I could just modify both. And one of them, nothing happens, right? I'm just being lazy here, right? Instead of checking, did you actually want to move x, change the x? Did you actually want to move y, change the y? Let's change them, because one does nothing. Right, so that should hopefully move for us here. So that's what we have to unit test, right? So let's go to unit test. Now, we've got a bunch of errors that could happen here, right? So ideally, to get 100% code coverage, we want invalid x and y, right? So this is fails both x and y, right? And then a fail if we try and move too far. So we'll arrange, select, and we'll assert. Right? And then so from infantry, import infantry. So we'll have an expected, really all we have is the expected failure here, right? So we need a unit here, so we'll make an infantry equals an infantry. Given it needs an x and a y, I don't know, 0, 0, and the team doesn't matter here, what we give it here is fine. And now we expect, so self.assert raises here. I think do we look at how to check for exceptions?
Try.
So you could do a try catch, but the assert raises will check that for you here. So you tell it what you're expecting to get back here. Say, hey, I'm expecting to get a value error when I call infantry.move given, I don't know, 1 and 1. So it should check, did we get a value error here when we call this function? And you don't have to do your own try catch blocks, which is nice. Thought we had looked at that, sorry. Oh, did I not do it right? Yeah, we got the error here. I need to specify. Sorry, Python assert raises. Unit test. Oh, where's my raises? Cert raises. Oh, it's with. Okay, sorry, with. I can never remember the syntax. Sorry. With self.assert raises. Value error? Infantry.move. All right, let's try that. There we go. So it's a little easier than the try catch block here. You just say with here, and that should do it for us. So really, there's nothing act where the act happens here when we're testing our tests or testing failures here. It's a little bit funky, but that should be okay here. Fails too far. So if I try and move 10, right, other one's okay, then we'll get another error here. That one passes, and then one where it actually works here, right? So we'll have a test move, can actually move here. So starting at 0, 0, we should have an expected x, then will be 5. We can move up to 5, right? So now we actually want to call our move here. So let's call infantry.move. Let's give it 5, 0, and then let's go get our actual location. So the actual x is our infantry get x location or x position here, and then self.assert equal my expected and my actual. All right, let's see if this one passes. All right, that one passes. All right, that okay so far? All right, we're running short on time. I got to talk about the next project here, but the other ones go the same way, right? We define what we need to define, and we test just the piece we need to test. I don't have to test any other things. Now, I could test the init and make sure I get out my actual 5 attack power, 5 hit points. We could test that. We could test the range as well, because the code runs when our other tests are running, but we didn't test did the values get set as what we expected here. Right, so it'd probably be good to do. Again, I don't particularly care if you did it or not, because technically we have the 100% code coverage, but this is why testing gets to be really interesting, because there's how far do I want to go with my tests to make sure that it does exactly what it's supposed to do. And usually we care if our code is right. So it's worth spending time testing. Did it do what I expected it to do? Right. It can take up a little bit of time, can be a little bit wordy, a little bit verbose, that sort of thing, but it's nice to have. And then once we've got the test coverage, it'll be there as things change in our classes and our game, because this is going to be such a fantastic, game here. You're still playing it 15 years later, like Skyrim, right? That sort of thing. Whatever. Uh, should we all be so lucky to make a game like Skyrim? All right. Let's talk about the next project here. So let me go make a new repository for you. And forgive me, I have to go steal this from last time, because this one was fun. 2001. Project 1. Use a Python template. All right, cool. Create. Let's make a new project. Project 1. Let me go open the other one here at the same time, so I can take the rubric too. Assignments, project 1. So 2 weeks, right? Puts us at February 12th, halfway through winter, right? We're getting there. 2 p.m. That's when class starts here. This one, I think I had 12 points in there. It's worth a little bit more. We do a little bit more stuff here. Here's your GitHub Classroom link. All right, so we're going to build a little checkers solving program here. You guys all played checkers? Okay. So it involves jumping pieces here. So you're going to have some sort of 2D list for the board, right? And you're going to assume the pieces are kings, which means they can jump forwards and backwards. Otherwise, that gets a little bit messy here. The board then will have a B for a black king, a W for a white king, and just a space for an empty space on the board. So you should be able to take any given board here, make sure that it's a valid checkerboard, and raise an exception. So valid checkerboards are 8 by 8, and then all the pieces are on the same color. I don't actually know or care if they're all on white spaces or black spaces of checkerboards, right? So if I give you a checkerboard, as long as all the pieces are on the same light or dark squares, we'll call it valid, right? That okay? Okay. And then we're going to have a function called get max jumps that returns the max number of jumps that any white checker can go, right? So when we think about a checkerboard here, checkerboard, uh, here we go. Sure. Oh, goodness. All right, that ought to do here. Let me start drawing on this here. So, oh, that's real weird looking, but sure. And where's my sketch tool? Snip tool. Come on. Oh, really? Just Shift S. Snip. Did, what?
If you paste
New? New. Thank you. It should put it to the clipboard. Okay, there we go. So we're going to imagine some checkers here. So if I have, say, a white checker here and a black checker here, the white checker can jump over the black checker, right? They can jump. That's how checkers works. If there's another piece here, it can't jump because there's nowhere to land. So it couldn't jump at that point here. So we go erase that one. If there's another black checker here and another black checker here, and let's put another black checker here, and let's put a black checker here, right? It can jump 1, 2, and get stuck here, right? It could jump 1, 2, get stuck here. It could jump 1, can't get to this one, right? So the max number of jumps then is 2. It doesn't matter that it's this direction here or this direction here. Right? The max is still 2. Right.
a total number of possible.
It's the longest possible number of jumps, right? It doesn't matter which chain it happens to be here, but we're going to test each one of these cases here, each checker. And if you've got more than one white checker here, right? Maybe I've got a white checker here, right? This one can jump 1, this one can jump 2. So the max jumps will still be 2, right? Now, if we added another black checker here and a black checker here, right? We could go 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps, and get back to this spot here, right? Or I could go 1 jump, 2 jump, 3 jump, 4 jump, 5 jumps, get back to the spot here. Right? Both of those work that way here. If we had more checkers around, right? Let's erase some of these ones here and say over this way maybe. Right? All the possible jumps I could do. I could go to here, 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 and here for 4 jumps. Works. 1, 2, 3, 4, 5 jumps. That's pretty good. Or 1, 2, 3, 4, 5, 6 jumps. Right? There's different paths. So with our recursive backtracking, we're just going to try it, see how far we get. Once we run out of opportunities here, right, when we reach a base case, we start undoing, we unwind. Right? So things that happen when you jump over a piece, the piece gets taken. Right? Otherwise, you'd end up jump, 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 jump. Make sure you're taking the piece off the board. Like we had to put down a marker when we were maze solving here to say, hey, don't go back onto this space here, right? Leave the breadcrumb. That was our modification. We did the 8 queens puzzle. We just took the queen back off, right? So when you jump over a piece, take it back off. To undo, you're going to have to put the piece back on, right? To undo that step. So a couple things that happen in there. So for points then on the rubric, let me get you, turn in a URL here. Excuse me. All right, so this is for project 1. Let me steal my rubric here. This worked out well. Oh, 15 points, sorry. We'll set it to 15. You get 5 points for taking your 2D board, validating it, right? And then we get 5 points for, come on, new criteria. Get max jumps working for 1 checker here, right? And then 5 more points for, no, this button here. Get max jumps working for all of our white checkers.
Oh, no test.
Well, you're going to want to know that it works here. I don't care if you want to do it in main or unit tests. Like you did it successfully for Project Zero, I'm assuming. I will write unit tests because that's what I like. You can do it in main if you want. It's okay. All right, so I'm going to use that one for grading here. Create the rubric, change it to 15 points. right? So 2D board validates it, should go pretty quick. We've done 2D boards before with our examples, but you make sure they're all on white squares or dark squares. There's some really quick arithmetic you can do for that, right? Because they alternate, right? And then it works for any one checker here, and then it will work for all of the checkers. You check all the white checkers. So you can have all sorts of crazy boards here. That's okay, right? Max jumps will be 0 or more, right? A valid board might also have at least one white checker and one black checker. Maybe not the end of the world if you don't check for that, because 0 jumps is still 0 jumps, but your code might be a little bit upset if you're expecting a white checker and there's not a white checker on the board. That sort of thing. Okay so far? All right.
Wait, checkers are there?
Sorry?
Is there 8 of each?
There can be as many as you want. There's a certain number that start on the board, right? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I wouldn't worry about how many. Like if you want to fill the board with them and no one can jump anywhere, sure. Call it valid and just no jumps.
Point sort of that we can input any board position.
Yeah. So init takes a 2D list here that will validate that it is a valid board. So it should be able to accept anything that looks like a checkerboard and has white and black pieces on it, and it's 8 by 8, and they're all in the same color. Yep. Awesome. All right. Sorry again to miss you.